there's a wire of length 2L, and we're interested in finding the electric field of this electrically charged wire at some point Z exactly above the midpoint here. Okay, so if we draw in our axes properly, as we always should, we have our X and Y axis, and we're interested in solving for the electric field at the position R equals 0, 0, Z. The electric field in general is given by the following formula. It's 1 over 4 pi epsilon 0 times integral of the charge density at location R prime divided by the distance of R from R prime squared, and it needs a direction, and that direction is the unit vector of R minus R prime, and the integrations over the points R prime, cubed because we're in 3 dimensions. Now in this particular example, the charge density of this particular wire, as it's confined only to the x-axis, it's going to incorporate that lambda charge density, which I didn't state, but has a charge density of lambda, and it's going to require some Dirac deltas here in order to confine it to that axis. Okay, so this is going to constrain y prime and z prime equal to 0, so that when we do this integration, we're only integrating along the x-axis. Then the electric field becomes 1 over 4 pi epsilon 0 lambda over r minus r prime squared, r minus r prime vector divided by r minus r prime dx. And now let's set up our actual coordinates. The r value that we're interested in, I wrote that down above, 0, 0, z. The r prime that we're interested in, well, that's our integration, and that's going to take place over x prime 0, 0, because those are the locations of the wire, and the integration is going to go between minus L and L. Okay, so that means that this vector r minus r prime equals minus x prime 0, z. The magnitude of this thing then is equal to the square root of x prime squared plus z squared. And now we can, well, by the way, let me just simplify this thing, because this is integral lambda over r minus r prime cubed in the r minus r prime vector direction dx prime. I put that in now fully. The electric field equals 1 over 4 pi epsilon 0 integral lambda over x prime squared plus z squared to the square root, which is power half, and then cube it, so 3 halves. And then I put in the vector direction minus x prime 0 z dx prime. So we have one integral for each of the 3 directions of the electric field. Happily, the y direction is 0. The z direction has something, and the x direction, well, if we notice the function involved here, if I write down what the actual integration is there, what the integrand is, it's basically minus x prime lambda over x prime squared plus z squared to the 3 halves. This is an odd function, which means it has the property that f of minus x prime equals minus f of x prime. In other words, it's kind of linear. It has a linearity to it. Doesn't mean that it's linear, because cubic polynomials are also odd, can also be odd, but what it means for this function in particular is that whatever it does in the positive half axis, it does the opposite of that in the negative half axis. So then if we integrate over an even domain from minus L to L, the area of the both halves is going to exactly cancel one another out, so that the x integral is just going to be 0. So that means this electric field has no component in the x or the y direction. And then you can come back to the diagram and think about, does that make sense? I should have called this the z direction when I made that diagram. So that's x, z, and then the y direction is out here. So we write down the full electric field then. Knowing all these things, 1 over 4 pi epsilon 0 times the integral of lambda z over square root, well, I won't put the square root, I'll use this 3/2 still, dx prime here, and I have a little z unit vector over there for my direction. So now at this stage, it just comes down to evaluating the integral. And at this point, it's pretty much a turning point, it's a fork in the road of how you're actually going to approach this. If it's real life, and real life isn't necessarily an exam, and you're allowed to use help, you'd go on Mathematica and you'd put this into Mathematica and solve it. But if it is an exam and you kind of need to know how to do these things, well then the question is, how are you going to do it? It can't be directly integrated. But there is a nice substitution you can do. And as for thinking about what substitution you're going to approach here, if you notice, I have my x prime here and a z here. So if I have for my substitution some sort of relationship that x prime equals z times a function of u, then when I plug that substitution into here, this whole term in parenthesis can receive some sort of factorization like z squared f squared of u plus 1. Now, if you know some trig identities, it'd be very nice if this f squared is a tangent squared, because if it's a tangent squared, then you have sine squared over cosine squared plus 1, which becomes sine squared plus cos squared over cos squared, which is 1 over cos squared. And because that's taken a square root and then cubed, but it's in the denominator, then the 1 over cos squared is going to become a cos squared in the numerator, which could be very, very good news for us. So let's do that. So then we let x prime equals z times tan of u, and I can get the differentiation dx du equals z sec squared u, and so I can just write dx prime equals z sec squared u du. Then I can put all of that into my little integral for the electric field, and I get 1 over 4 pi epsilon 0 integral lambda times z divided by z squared tan squared u plus z squared to the 3/2 times the dx prime, which I now write as z sec squared u du. And as for the limits, I know they're from x goes from minus L to L, so I'll just leave that for later. I don't necessarily care at the moment for writing them in terms of what the u values are. So I just want to simplify this now. I'll leave out this prefactor, I don't have to write it down every time. Lambda z squared divided by, let's see, so there's a z squared to the power of 3/2 that factors out from all the rest of this, which remains as tan squared u plus 1 to the 3/2. And then I have a sec squared, which I like to write as cosine squared u because I don't like sec. So that becomes lambda z squared divided by z cubed. Now this tan squared plus 1 I mentioned earlier was 1 over cosine squared. 1 over cosine squared u to the 3/2, 1 over cosine squared u du. And now this is looking promising, because this will cancel, and this becomes 1 over cosine cubed, which goes on the numerator of the cosine cube. Well, let's just, do it, which is much better than talking about it. So that's the first term, lambda over z. Now 1 over cosine squared u. It's 1 over cosine cubed u, which becomes cosine cubed in the numerator, and we'll cancel with this cosine squared. And then I'm left with lambda over z times cosine u du. Now this is looking nice. And this is easy enough to integrate. So now let's see, can we do some sort of conversion here now for the u's? I'd rather not, to be honest, if I can get away with it. Let's just see. 1 over 4 pi epsilon 0 lambda over z times sine u. Sine u equals whatever it is to u equals whatever it is. So now let's work out what the limits are. So if x equals minus L, or x prime equals minus L. Then we have minus L equals Z tan U. So we have tan U equals minus L over Z. So what this means is that there's a triangle where there's an angle here U, and the tangent of that angle is minus L over Z. Tangent is opposite over adjacent, L over Z. So I'm going to need the sine of that angle. So the sine of that angle, right, that's what I have here, is going to be opposite over hypotenuse, L over, so minus L over square root Z squared plus L squared, right? That's the hypotenuse. And if x prime equals L, then it's the same thing, except for this, instead of being a minus L, is a plus L. And we could have known that this thing will double up because of the fact that, unlike the original, the x component here was an odd function, but the z component is an even function. It has the property that f of minus x prime equals f of x prime, right? Which means that it's whatever it does in the left hand side is going to do the same. So if I integrate from minus L to L, it'll just be double the integral from 0 to L. Okay, so that's, you know, one thing we could have seen earlier on. But, you know, sometimes that's how problem solving goes. You don't know everything the first time around, and you may not notice it. But hopefully you do. So this is going to give me 1 over 4 pi epsilon 0 times lambda over z. Lambda over z, I'm going to have the positive one minus the negative one, right? So it's 2L over square root z squared plus L squared. And I'll write everything down properly in the z hat direction. And then I can just simplify this a little bit. Right, that'll cancel. That becomes a 2 lambda L over 2 pi epsilon 0 1 on z squared plus L squared. Okay. And I believe that is the correct answer. And what's interesting always with these sorts of problems is you look at the limiting cases. For instance, if L goes to infinity, what happens there? Well, we'll have to do a little bit of work to make a sort of an expression that's not indeterminate, right? We can't have infinity over infinity. So let's look at this, let's look at this in another form. Lambda over 2 pi epsilon 0 times 1 over z times L over square root z squared plus L squared. And now what I can do with this term is I can imagine I factor out an L out of here, and I factor out the L squared out of all of this, which comes out of the square root and becomes L square root z squared over L squared plus 1. Now these can cancel, and I'm left with an expression that's square root 1 plus z squared over L squared. In the limit as L goes to infinity, this expression, what happens to that? Well, you know, it's just 1. So in the far or in the limit of an infinite wire, an infinitely long wire, we find that the electric field points solely in the z direction. Let's not forget that, and it has the magnitude lambda over 2 pi epsilon 0 1 over z in the z direction. And there you go. Pat yourself on the back. You've now found the electric field of a wire of length 2L, as well as the limiting case of an infinitely long wire.